So today we're going to learn about ratio and proportions and also dimensional analysis, which is also referred to as the factor label method. First, we're going to start off with ratio and proportions. So a ratio is a relationship between two amounts, showing how one value is a part of another. So this can be shown with fractions, decimals, or percentages. So some examples here, we have 80 over 100, 80 out of 100, 0.8 in its decimal form, and then 80%. If it's a single digit like 6, we would show it basically the same way, except for when we get to a decimal form, we would show it as 0.06 rather than 0.6. 0.6 would be if it was 60. A proportion is the setting of two ratios equal to each other. So this allows us to do things like solve for x in the following problems. Now, when we're setting up our actual ratios, we don't necessarily have to worry too much about what number is in the numerator and which one's in the denominator position, as long as we align our units with this type of problem. However, it is good to be in the habit of writing your weight-based units at the top and your volume-based units at the bottom. Sometimes you might have weight, and volume, and that's okay. But in general, it's good to be in the habit of this just because when we get into percentage math later, that will be very helpful if you're already in the habit of writing weight over volume. Okay, so the rules with ratio and proportions. The first rule is to make sure that you are given 3 amounts and need to find a fourth. Later, when we compare dimensional analysis with this, we'll learn that dimensional analysis does not necessarily need this 3-amount rule. This is specific to ratio and proportions. I prefer the ratio and proportion method, even though you have to solve several equations, maybe if you need to do several conversions, because to me, it's just easier to break it down that way. Dimensional analysis, you can solve many equations at once. And to me, that gets a little confusing. It's just helpful for me to only use it for IV drip rate conversions, but otherwise, I prefer ratio and proportion. So our second rule is to make sure that you have 2 different units. Sometimes you might have the same unit for 2 different things. You could count that as, 2 different units. And if you have more than that, so let's just say maybe you have weight and volume, and you have 2 different weight units, so one's in grams and one's in milligrams, you'd want to make sure to use that acronym that we learned in the previous lesson, King Henry died by drinking chocolate milk, to convert your metric units to make sure that you have either grams and grams or milligrams and milligrams. You don't want to go into this having both. Our third rule is when comparing our ratios, our units in the numerator and the denominator match exactly. We'll learn that when we get into dimensional analysis, that's not necessarily the case. It's quite opposite, actually. But here, we want to have it matching. So, an example, numerators are the top part of a fraction, and denominators are the bottom. So, what we want is to see something like this. Numerator over denominator equals numerator over denominator. And then we want the same units in the denominator. And let's do grams at the top. So grams. So we want like units. So here we have the same units for our numerator and then the same units for our denominator. One of these units, however, is going to be our x, since we're trying to find 3 numbers and then solving for the fourth. So as an example, let's just say this is our x. So this is our x unit, and then the rest of these units were given somewhere. Usually this would be your whole given amount, and then this would be the part that you're trying to find. So to find, and then this is your actual given. So I always say with ratio and proportion, you take what you know or you're given, and you set it equal to what you're trying to figure out. So once you fill in your 3 numbers and your x for the fourth, then you cross multiply to solve for x. So here, since we're setting equal, we can cross multiply. So in the end, you're going to want to see something like ND, because you're going to multiply the numerator and denominator, and then the next numerator and denominator, setting each other equal. So ND. So that's what you're going to want to see. So moving on to some examples. Our first example here. So let's say you're making some rice. You know that each cup of rice requires 1.5 cups of water. However, you're cooking for some friends and want to make 4 cups of rice. How many cups of water would you need? Okay, so right here, you know that each cup of rice requires 1.5 cups of water. So that's your given. However, you're cooking for some friends and you want to make 4 cups of rice. So that's what you're trying to figure out. It's the 4 cups of rice part. How many cups of water would you need? So this is also what you're trying to figure out. And that's your x, because it's asking how many cups of water would you need. So they don't know that yet. It's not given. So this is your x right here. So let me just set that up real quick for you guys. One cup of rice. Here, it's given in the form of 1.5 cups. But as we learned over here, with ratios, you can represent them a little bit differently, depending on how it works best for you. I am going to take that 1.5 cups, because that's confusing for me, especially if I'm putting it already into a ratio. I'm going to translate that to 1.5. So I'm going to translate that to its decimal form, just to make it a little easier. So 1 cup of rice per 1.5 cups of water. I'm going to set that equal to what I'm trying to figure out. So this was my given. And what am I trying to figure out? So I'm trying to figure out how much water. So we already know that's our x. So even if for some reason you can't find the other part of your given, you can put x and then you at least know what you're looking for. So the other part I have in what I'm trying to figure out is 4 cups of rice. And now we cross multiply. So 4 times 1.5 equals 6. That's right. Now numerator times denominator is 6 equals, and then we're going to multiply x to 1. So 1x. Now we want to isolate x. So we're going to divide both sides by what's attached to the x, which is the 1. And so we get 6 equals x. So that means that 6 cups of water are needed to make 4 cups of rice. So notice that all the units in this equation right here were cups. So that's why I had to specify cups of rice, 2 cups of H2O, because you want to make sure that you make it obvious that you have the right unit in your denominator, because you need to align units. So here I have cups of rice in the denominator for both, in the numerator for both, and then cups of water in the denominator for both. So x would be cups of water. I think it's just good practice to write it out. So I could just write 1 cup, 1.5 cup, whatsoever. But it's good practice just to write it all out. That way you can make sure that you're really aligning those units, especially if you're first starting off. Okay, so moving on to example 2. So example 2 is where we get more into actual pharmacy stuff, working with medications. So here we're going to apply some basic math to a common pharmacy problem that I had to solve daily when working for a home infusion pharmacy. Let's say you get a work order. So work orders are what prescriptions are called in the home infusion setting. We'll learn later throughout the class that depending on the setting you're working in, prescriptions might be called slightly different things. This work order is for daptomycin, which is an IV push antibiotic. The work order asks for 7 syringes, each 12 milliliters. So here I'm just going to highlight that just because we're going to need to know that later. So 7 syringes, each 12 milliliters. So Dapto often comes in vials of 500 milligrams. To make these vials ready for the patient, the pharmacy technician must reconstitute, which would be to dilute and mix into a solution. So you can reconstitute into a solution or suspension. For IVs, we always need it to be a solution. Solution means that the particles are fully dissolved. We don't want any chunks going into our veins. A lot of times for antibiotics that are drinkable, you'll see them in suspension form. If it's a suspension, that means the particles aren't fully dissolved. That means that they can settle to the bottom, which means that as a pharmacy technician, you'd want to add an auxiliary sticker to that prescription reading shake well before use or whatsoever, just to make sure you get that the particles fully distributed before the patient pours it to then take it. So that way they get a correct dose. Okay. Where were we? Okay, so to dilute and mix into a solution, the 500 milligrams of powdered Dapto with 10 milliliters of normal saline. Normal saline is 0.9%, pretty much you could say salt water. In this case, it would be sterile water. Due to this, we know that each vial will have about 10 milliliters inside. It might have a little bit of what's called overfill. That's a little bit of extra liquid to help the technician get all of the liquid needed out of the vials. But we're not going to count that in this particular equation. So when reconstituting is finished, we'll have about 10 milliliters out of that 500. So with this in mind, how many vials would need to be given to that technician to then reconstitute to fill the prescription properly? So our given here, I know I gave you guys a lot of information, but our given was that for every 500 milligrams of Dapto in these vials, we're going to end up creating 10 milliliters of solution. Basically, just to recap on why this happens, is that, let me just draw this. Oh, I'm still in highlighter, sorry. Here we have our vial. Excuse my bad drawing. And that's going to be our vial of Dapto. So basically, antibiotics are usually shipped out in powder form because antibiotics a lot of times don't have the best shelf life. So they're shipped out in powder form because once you add that liquid to them, they're only good usually for about 7 days. So in order to have the better shelf life, they're just sitting on the shelf in a powder. And once you add that diluent, in this case, it would be saline, then they're mixed up into that solution form. So that's why you have a little bit of drug per whole solution. So that's why we always want to take amount of drug. That's why the whole thing, it's not just 10 milliliters of medication. We only have the 500 milligrams of that powder first. So here we have that 500 milligrams of medication. And then we're adding in 10 milliliters. It doesn't really affect the overall volume just because 500 milligrams is quite small. So that's why we still end up having a total volume of 10. Sometimes, if we have a little bit more powder in that vial, there might be a small difference in the overall output of the volume, which we'll see in the next example, and I'll go over that when we get to that. But for now, enough with that. Let's get to the actual problem. So our given, as we went over a lot, is 500 milligrams per 10 milliliter. That's our given. First, we want to figure out exactly how much medication we need to even make. So right here's our work order. Right here. So 7 syringes, each 12 milliliters. So get this out. 7 times 12. So when you do 7 times 12, we get 84 milliliters. So this is the total amount of medication we need to make to fill that order. If we're only making 10 milliliters at a time, each time we're making vials, that means that we would have to make 9 vials in order to even make 84. If we made 8 vials, we would only end up having 80 milliliters of medication, which wouldn't be enough to fill that order. So we would make 9 vials. So then we would have 90 milliliters. So we would make 90. So that would give us with 6 milliliters waste. And in a pharmacy setting, we don't write the waste is just the milliliters, because remember, that's not the amount of medication that we have in here. The amount of actual drug per 10 milliliters is 500 milligrams, are given. So we need to figure out exactly how many milligrams is in 6 milliliters, because when we're writing off waste in a pharmacy, we need to say how much drug we're wasting, not how much solution we're wasting. So taking our given right here, starting off right here again, I'm going to set that equal to 6 milliliters. And we're going to put X at the top because we're trying to figure out how many milligrams is in 6 milliliters. So cross multiplying. I'm going to erase this stuff just so we can start working right there. So if we cross multiply, 500 times 6 is 3,000 equals 10x. Once again, we want to divide both sides by 10. And then we would get 300 milligrams equals x. So that's how much waste we're actually having with that 6 milliliters. So we want to see, does our answer make sense? So for every 10 milliliters, remember, we have 500 milligrams. So if we have 6 milliliters, which is a little bit smaller than 10, we're going to have a little bit smaller than 500 milligrams. 300 is a little bit smaller. So at least we can see that that amount, our answer, makes sense. And if you guys were curious, this is where I kind of went along with, does this make sense? So okay, so example 3. Another common antibiotic I had to prepare in the home infusion pharmacy was ceftriaxone. To prepare this, we would more often work with 2-gram vials and add in 19 milliliters of sterile water to reconstitute. And once this became that solution, because, it needs to be a solution to go into any kind of vein, we would be left with 20 milliliters. So this problem is exactly what I was talking about earlier when I said sometimes once we add in our diluent, we might have a little bit more a total solution. So here is the amount of medication. Here's the amount of diluent. And then here is the total amount that we'll have. So in our given, we wouldn't have 19 milliliters. We would have that 20. Let's just say, for example, that we wanted to figure out how much volume that actual powder of medication is making. So in the last example, daptomycin, it wasn't making anything. Remember, we added in 10 milliliters and then we were still left with 10 milliliters. In this case, it's a little bit different. So in order to figure that out, you take the 20 from your given, and then you subtract it by how much you add. So we added 19 equals so here, if we were trying to find out our powder volume, that would be our powder volume. So powder volume. So powder volume, once again, that is the total amount that you're left with of solution, so 20, subtracted from the amount of diluent that you add in. And that's the volume that this is. Okay, well, moving on. Okay, so basically, there are also 1 gram vials of ceftriaxone to use. This example is basically for if we're out of stock in 1 grams, if we ran out for some reason, if for some reason our pharmacy didn't order the 1 grams, then we could always use the 2 grams and just end up with a little bit of waste if we needed to fill that prescription right away for the patient. Okay, so going back to our little highlighter, this prescription calls for 7 syringes, each of 10 milliliters. So let's figure out what that looks like. So 7 syringes, each 10 milliliters. So we do 7 times 10. So this prescription wants 70 milliliters total. And remember, when we're making the ceftriaxone, we're making 20 milliliters at a time. So we can make 60 milliliters, and then we can make 80, but we can't make 70. So what are we going to have to do? We're going to have to make 80, because 60 is not going to fill this prescription. So 80. So that means that we're going to have to reconstitute 4 vials. We're going to make 80 milliliters. And we're going to have 10 milliliters waste. Okay. So let's figure out what that is. So we have 2 grams over 20 milliliters. Remember, that's our given. I'm getting that from right here, at the top right here, our given. Set that equal to the amount of waste we have. Obviously, this is math that you could probably do in your head. I'm just writing out all these steps just because eventually it will get to the point where it might be more difficult to do in your head, so that way you know how to figure things out. So setting equal to the amount of waste that we need. So right in here, we're going to waste 10 milliliters. So setting that equal to 10 milliliters. And then we don't know how many grams this is in this 10 milliliters. So let's cross multiply. We have 20x set equal to 20. Divide both sides by 20. Then we get x equals 1. gram. So 1 gram of waste with that ceftriaxone order. Okay, so now the problem is saying, let's just say the pharmacist does not want the waste in grams. Let's say the pharmacist wants the waste in milligrams. What are we going to do? So we're going to go back to our metric conversions. So we're going from grams to milligrams. Grams, remember, is our base unit for weight. Milligrams is the last unit here. So 1, 2, 3. We went 3 units to the right. So let's take our 1, decimal points right here, because it's a full number. 1, 2, 3, fill in zeros where our loops are. We have 1,000 milligrams. And that's what we would tell the pharmacist our waste is if they wanted the waste in milligrams for ceftriaxone. Okay, moving on to example 4. Okay, so let's say you're reconstituting an oral antibiotic for a child in a retail pharmacy. You know that one bottle has 120 milliliters of antibiotic suspension. So remember, if it's oral, we can do suspensions, which isn't fully dissolved. If it's an IV, we would have to do solutions, which is fully dissolved for the child. But you're curious to know how many bottles would make a full liter. To do this, you would set up the equation. So right here, as you can see, our given was right here. So one bottle has 120 milliliters. So that's why we write right here. One bottle, 120 milliliters. What you're trying to find, you set equal to. So we're trying to find how many bottles. So once again, like units are at the top. The problem here, however, is 120 milliliters of suspension is set equal to 1 liter. Remember, we have to have complete like units. So even though the bottom are both liquid units, they're not the same. We need either milliliters and milliliters or liters and liters. So as you can see, we translated that to milliliters. So show you guys, King Henry died by, put that in a square, drinking chocolate milk. And we're going from liters to milliliters. So our base over to milli. 1, 2, 3. So 1 liter to milliliters would be 1,000 milliliters. So now we can solve. So setting 1 over 120 equal to x over 1,000. Cross multiplying. And we get that 8.3 bottles are needed to make 1 liter. Okay, so we're going to start comparing ratio and proportions to dimensional analysis. So the rules for dimensional analysis would be to place the same units diagonally from each other so that they cancel out. So that's the opposite of ratio proportion, where you want to line like units. Second rule is the unit that you want to be left with needs to be in the numerator position. And I'll show you that in a second. Rule 3, if a denominator isn't given, assume it's 1. And rule 4, multiply numerators and then denominators, set as a fraction, and then divide. So, remember when we went over ratio and proportions, I told you guys a numerator over denominator is set equal to numerator over denominator. And remember, the numerators both have to have the same units. The denominators both have to have the same units. And one of them is going to be x. So let's just assume it's this one. But any one of these really could be our x. And that this first amount right here is going to be our given. That's pretty much how ratio proportion works. Dimensional analysis works by crossing out units. So here we're going to have a number that we start with. Multiply. So we don't set equal in dimensional analysis. Here we set equal in ratio proportion. We set equal. Dimensional analysis, we multiply it by our given. And we set up the given to make the units cancel. So whatever unit this is needs to cancel with this. And this unit right here needs to be what we want to be left with. So we want to be left with whatever unit is in the numerator position on the right. So unit to be left with. Okay, so now let's just look at the examples and compare them, since I did the same examples for each one. So with the rice problem that we went over earlier, as you can see, with ratio proportion, we have our equal sign, we have our given, and then we have the equation of what we want to find. Here we have the x. We have units aligned, so the numerator is going to have cups of rice, both the same unit. The denominator has cups of water, both the same unit. And here we cross multiply. Looking at dimensional analysis, we have cups of rice is our starting, because that's not the unit that we want to end up with. This is the unit we want to cancel out. So this is cancel out unit. Want to cancel out. This is the unit that we want to keep. So we want to find cups of water. So cups of rice is set diagonally to cups of rice. So these units cancel, and then we are left with cups of water unit. That's how that works. So here we're going to multiply 4 times 1.5. Our answer is 6. And then we put it over 1, because 1 is right here. And then we divide that. So you want to cross multiply. If there's more than one amount on the denominator, you would once again, sorry, not cross multiply, multiply across. Then you would multiply across on the denominator, and then you would divide those amounts. Okay, so going to that second example. Once again, just to see it here, the amount we want is milligrams of Dapto. Remember, 6 milliliters. That's how it looks in ratio proportion. But here we don't set up like units on both sides. Here we put them across so they cancel out. Once again, you always want the units that you're trying to find in the numerator on the right. So units you're trying to find must be in the numerator on the right-hand side. So that way you can easily cancel these out. So milliliters of solution cancels out, milliliters of solution cancels out, and you're left with this unit, milligrams of Dapto. Remember, you're multiplying across. Not cross multiplying, but literally multiplying across with dimensional analysis. So you would want to multiply that 6 milliliters to 500 milligrams. And then you'd want to divide that by your bottom unit right here, which is 10 milliliters. So example 3, once again, canceling out milliliters of solution. and you're going to be left with that grams of self-trioxone. So as I said, I usually prefer ratio and proportion. I think it's easier. But here's an example of when dimensional analysis could be quite handy. So when you're doing multiple conversions at once. So here's an example that you might use when baking, but to show you guys, ratio proportion, remember I told you guys in the beginning that you would have to have 3 givens units, and then you would be trying to solve for a fourth. Dimensional analysis doesn't have that problem. You could just keep going. So let's say I want the amount of butter being used in grams for this recipe. So right here I have 4 ounces of butter for that recipe. So if I want that in grams, I know that there are 154 grams in a pound, and I know that there are 16 ounces in a pound. So using those 2 different conversion factors, I can figure this out using dimensional analysis. So here we have ounces of butter that cancels with this ounce. So I'm left with pound right here. Pound cancels right here. So then I'm left with gram. And that's what we wanted to find. When we get into the IV drip rates and all that later, you'll see that it's really important to be able to, do this process of continuing to cancel units. Okay, so here we have a homework problem. So, for example, 45 milliliters. We have that. And from there, we want to know TSP, and then we want to know TBSP. So we can figure this out using ratio, proportion, or dimensional analysis. I'm going to show you guys ratio proportion, just because I told you that's my fave. So we're going to take our given to do this, because that's what we do with ratio proportion. So here we're going to TSP first. So here I have my conversion right here, and that would be my given. So our given here is 1 TSP over 5 milliliters equals X TSP, because remember that's what we're trying to figure out right here, over 45 milliliters, which is right over there. Cross multiply 45 equals to 5x. Divide both sides by 5. And we get 9 equals x. So our answer here is 9 TSP. And then we have another conversion factor here. Now here we could do either one of these. We could either convert from our 9, or we could go and convert from our 45 again, because we have both the conversion factors. Now let's just continue on. Let's convert from our 9. So we have 1 TBSP to 3 TSP. And we have 9 TSP. And we're trying to figure out that TBSP. So that's where our X is, and we're setting that equal to each other because this is ratio proportion. So cross multiplying, 3x equals 9. Divide both sides by 3. And you get 3.